All right, so some formulas for tangent. Now, you can take these just as given, or what you can do is, whoops, backslide. I just wanted to go to the pen. What you can do is you can say the following. The tangent of alpha plus beta is the sine of alpha plus beta over the cosine of alpha plus beta. And since we have some formulas for each of those, this is sine alpha sine beta plus, no, sorry, it's sine alpha cos beta. Let me erase some stuff so that it's actually correct. Sine alpha cos beta. I'm just applying the sum formula for sine, which mixes up things. Sine alpha cos beta plus sine beta cos alpha. The sum formula for cosine is cos alpha cos beta minus sine alpha sine beta. Okay. Now, there's a lot of stuff I could do here. What I'm going to do, if it would stop assuming I wanted to go forward, what I'm going to do is I'm going to multiply the numerator and denominator by 1 over cos alpha cos beta. Don't wonder why I would do it. Just acknowledge that basically all I did was multiply by 1. I'm dividing the numerator and denominator by the same thing. So what I end up with is sine alpha cos beta over cos alpha cos beta plus sine beta cos alpha over cos alpha cos beta. That's my numerator. Now my denominator is cos alpha cos beta minus sine alpha sine beta, and I'm going to divide both of those by cos alpha cos beta. I'm apologizing for the kind of illegible writing, but we're about to cancel it out anyway. So notice that this term here is cos alpha cos beta over cos alpha cos beta. So that's just 1. This term here is sine alpha over cos alpha, sine beta over cos beta. So that's exactly tan alpha tan beta. And up in the numerator, I can cancel a cos beta here, and I can cancel a cos alpha here, leaving behind exactly tan alpha plus tan beta. So this formula is not pulled out of nowhere. It's actually an identity you can derive from the sum formulas for sine and cosine. So what could be, I'm going to erase all this, a very handy sort of practice is use the difference formulas for sine and cosine to try to establish this identity for tangent. Okay, but let's use various things to establish this identity. Tangent of theta plus pi is tangent. Observe, we know this already. Tangent has period pi. That's what this is saying. Okay, but way back when, it wasn't immediately clear why tangent had period pi, because sine and cosine have period 2 pi. So why does this one have period only pi? Well, let's see. Using the sum formula for tangent, I expand it out like this. Okay. And then the tangent of pi is 0. And we get just tangent of theta. Perfect. Okay, so here is a nice little way to establish that tangent has period pi. As long as you are willing to believe the sum formula for tangent is true, then yes, tangent has period pi. Okay, how about this identity here? Again, the left-hand side is the tangent of a sum, so we're just going to apply the sum and difference formulas for various things. Okay, honestly, I think you could have gone right from the sum formula for tangent. I don't know why the book wants now to split it up as sines or cosines, but okay, we can. So in the top, we're using the sum formula for sine, and then in the denominator, the sum formula for cosine. And then we can use various things like the sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So this is going to simplify right back down to cosine over negative sine, aka negative cotangent. So if you take tangent and you shift it left by pi over 2, it becomes negative cotangent. Yeah, the graph of cotangent is a vertical reflection of the graph of tangent. Remember, one went like this and the other goes like that, but it's also shifted by pi over 2. Yep, that checks. Okay, now here's an interesting one. Find the exact value for the sine of arc cosine of 1/2 plus arc sine of 3/5. So I'm going to pause to give you time to do this. My hint is start by using the sum formula for sine and then go from there. So pause here and see what you can come up with. All right, hopefully we did our best. Okay. We can actually simplify our way of writing it if we just let arc cosine of 1/2 be the angle alpha and arc sine of 3/5 be the angle beta. So then that means the cosine of alpha is 1/2. Okay. Also, because alpha is an arc cosine, it's in quadrant 1 or 2, it's between 0 or pi. Similarly, because beta is an arc sine, it's between minus pi over 2 and positive pi over 2, and the sine of beta must be 3/5. Okay. So then what we can do, since I'm going to flip back, sorry. So what we know is, we know cosine alpha, but what's the sine of alpha? And we know sine of beta, but what's the cos of beta? Since alpha is in quadrant 1 or 2, the sine of alpha is definitely positive, and since beta is in quadrant 4 or 1, the cosine of beta is definitely positive. So we can use Pythagorean identities to say the cosine of alpha is 1/2. Then I can get the sine of alpha is plus or minus something, but it's got to be plus because we know we're in quadrant 1 or 2. If the sine of beta is 3/5, then the cosine of beta will be plus or minus something, but since we're in quadrant 1 or 4, it's got to be positive. So that's what we're going to do on the next slide. So we're going to use Pythagorean identities to say the sine of alpha had better be plus or minus the square root of 3/4, but again, because we are in quadrant 1 or 2, it's definitely positive, root 3 over 2. Similarly, cosine of beta is going to be plus or minus 4/5, but since we are in quadrant 1 or 4, the cosine is positive. So cosine of beta is 4/5. Why would it be handy to say, now we have sine alpha, sine beta, and we have cos alpha, and we have cosine beta. Now we know all 4 of these. Why is that handy? Because we were asked, compute the sine of alpha plus beta. And when you apply the sum formula for sine or cosine, all 4 terms end up being important. You need the sine of alpha and the cosine of alpha and the sine of beta and the cosine of beta. So that's why we started off the problem by finding all of those missing bits. We plug in everything we want, we have a common denominator of 10, and there we have the result. So can you do the similar kind of computation but without a particular number in there? Write the sine of arc sine of u plus arc cos of v as an algebraic expression involving just u and v but no trig functions left. So we want to do more or less the same thing, okay? So specifically, let's say alpha is arc sine of u, therefore the sine of alpha is u. What's the cosine of alpha? It's going to be plus or minus the square root of 1 minus the sine of alpha squared. Okay. Well, pardon me. Sine of alpha is u, so this is plus or minus the square root of 1 minus u squared. But now quadrant restrictions can help us narrow that down. Alpha is an arc sine, so alpha is in quadrant 1 or quadrant 4. Either way, its cosine is positive. So cosine of alpha has to be the positive square root of 1 minus u squared. Okay, so that's nice. We have, I'm just going to keep track up top in this little narrow sliver. We have the sine of alpha is equal to u, and the cosine of alpha is equal to the positive square root of 1 minus u squared. Now let's come over and say beta is the arc cosine of v. That means the cosine of beta is v. Okay, that's handy to write down. Because ultimately, when we're going to use our sum formula for sine, I'm going to have a sine of alpha, a cos of alpha, a sine of beta, and a cos of beta. So let's write everything down. Okay, so then we ask, what's the sine of beta? Well, it's the square root, it's plus or minus the square root of 1 minus cos squared beta, which is plus or minus the square root of 1 minus v squared. And again, quadrant restrictions are going to narrow this down. Since beta is an arc cosine, it's in quadrant 1 or quadrant 2. Either way, the sine is positive. So the sine of beta is just root 1 minus v squared. Okay, so I'm going to write that up here in our little note-keeping spot. The sine of beta is the square root of 1 minus v squared. 1 minus. Now I'm going to erase a bunch of our work. Okay, pause here to copy stuff down if you need to. Okay, so let's clear things up. Ho-hum, ho-hum. Okay, I'm leaving up that alpha is defined as the arcsine of u and that beta is defined as the arc cosine of v. Because now what we're going to do is we're going to use the sum formula for sine by plugging in these alphas and betas. So what we need to compute, or simplify rather, in this problem is the sine of arc sine of u, that's alpha, plus arc cos of v, that's beta. Hey, that's a sum formula for sine. So this is sine alpha cos beta plus cos alpha sine beta. Beta. Okay, what's sine alpha? U. What's cos beta? The square root, oh, sorry, it's just v, so u times v. What's cos alpha? The square root of 1 minus u squared. What's sine beta? The square root of 1 minus v squared. And there you have it. This might be combined into a single square root once we look at how the book solved it, but this is basically it. We have an algebraic expression for the sine of the arcsine of u plus the arc cos of v. And notice at the end here, there are no trig functions left, just a bunch of algebra involving u and v. So pause here to copy if you want. I'm going to erase it and we can see how the book did it. Okay, so observe, they're just letting alpha be arcsine u and beta be cosine v, arc cosine v, sorry. Okay, they're just observing what quadrants things are in. Therefore, the cosine of alpha is positive, so we can take the positive square root. Sine alpha was u, there we have it. Okay, so the sine of beta is positive, so they just take the positive square root, that's square root of 1 minus v squared, just as we did. Then they do the sum formula for sine and get exactly what we got. Great. Okay, so we're going to end this video here. In the next and final installment for section 7.5, we'll come back and we'll just do more problems, but now we'll start solving equations that have sines and cosines in them.